Imagine a world where machines don't just follow instructions, but understand context, anticipate needs, and reason through problems like a human. This isn't science fiction. It's the frontier of artificial intelligence today, and at its core lies a revolution in how models process information, the rise of reasoning models. For years, large language models were trained to predict the next word. They became astonishingly good at mimicking human language, writing essays, coding, even composing poetry. But here's the catch: they didn't understand. They were pattern matchers, not thinkers. When faced with a complex problem, like solving a multi-step math puzzle or diagnosing a medical condition, they'd often hallucinate, jump to conclusions, or fail entirely. But now, a new generation of models is emerging, ones that don't just generate text, they think. These are reasoning models, and they're rewriting the rules of AI. So how do they work? Let's dive deep. At the heart of this transformation is a technique called chain-of-thought prompting. Instead of asking a model, "What's the answer to 37 times 42?" and getting a single number back, you ask, "Show me your reasoning step by step." The model responds. First, break 37 into 30 and 7. Then 30 times 42 equals 1,260. 7 times 42 equals 294. Now add them. 1,260 plus 294 equals 1,554. This simple shift, requiring a step-by-step explanation, has been a game changer. Why? Because it forces the model to simulate a human-like thought process. It's no longer just retrieving a memorized answer. It's performing a sequence of logical operations. But here's where it gets even more powerful: self-consistency. Instead of generating just one chain of thought, the model runs multiple trials, each time thinking through the problem differently. Then it compares all the answers and picks the one that appears most frequently. This isn't just about accuracy, it's about robustness. It reduces errors from random noise or flawed reasoning paths. And this isn't just theoretical. In benchmarks like GSM 8K, where models solve grade school math word problems, models using chain-of-thought reasoning outperform traditional models by over 30 percentage points. Some now achieve near-human accuracy. But what if we could go further? What if the model didn't just generate reasoning, but refined it? Enter RAACT prompting, a hybrid approach that combines reasoning with action. RAACT stands for reasoning and acting. Instead of just thinking in silence, the model decides when to take action. For example, if it's trying to answer a factual question like, "Who invented the telephone?" it might reason, "I know Alexander Graham Bell is associated with the telephone. But to be sure, I should look it up." Then it simulates a web search, retrieves the correct answer, and confirms it. This is huge, because now the model isn't limited to its internal knowledge. It can interact with external tools, databases, APIs, code interpreters, just like a human researcher would. It reasons, it acts, it verifies. And when you stack these techniques together, chain of thought, self-consistency, RAACT, you get systems like DeepSeek R1, GPT-4o, and Gemini 1.5. These models don't just answer questions. They solve problems, debug code, design experiments, and even plan multi-step strategies. But here's the real breakthrough: reasoning as a learned capability, not just a prompting trick. Early models needed human-designed prompts to reason. But now, researchers are training models to internalize reasoning as part of their core architecture. This is done through self-supervised learning on reasoning-heavy datasets, like math problems, logical puzzles, and scientific reasoning tasks. The model learns to generate chains of thought not as a trick, but as a default mode of operation. Even more advanced, tree-of-thought-to-T reasoning. Imagine a model doesn't just follow one path of logic, but explores multiple branches, evaluates them, and chooses the best one. It's like a decision tree, but built into the model's reasoning process. It can backtrack, try alternative approaches, and even self-correct when it hits a dead end. This is where we're seeing models outperform even their own previous versions on complex tasks, like designing a new algorithm, proving a theorem, or navigating a multi-agent simulation. And the hardware? It's catching up. Modern GPUs and TPUs are now optimized for the kind of long, sequential reasoning paths that these models require. With attention mechanisms that scale efficiently and memory architectures that support long context windows, some models now handle 1 million tokens of input. Reasoning isn't just possible, it's practical. But let's be clear, this isn't magic. It's math. It's statistics. It's massive data, massive compute, and massive insight into how intelligence emerges from patterns. Still, challenges remain. Reasoning models can be slow because they're processing many steps. They can still hallucinate when faced with ambiguous inputs. And they don't truly understand in the way humans do. They simulate understanding through statistical coherence. But the progress is undeniable. We're moving beyond language models that predict words towards systems that reason, plan, and adapt. And this shift is already transforming fields, from drug discovery and materials science to education and software engineering. The future isn't just smarter AI, it's thinking AI. So the next time you ask a model a complex question, remember, you're not just getting an answer. You're witnessing a machine think. Step by step. Reason by reason. And that right there is the dawn of real artificial intelligence.